we've talked a little bit about acceleration in terms of the graphing, right? We looked at velocity versus time graphs, which tell us acceleration via the slope, correct? Okay, slope of a velocity versus time graph tells us acceleration. So now we're going to get into a little bit more about what is acceleration and how we see it kind of in the everyday world, okay? Acceleration at its most base form is a change in velocity, right? It's some sort of change in velocity. So as we've seen it on a graph, right, if I have a velocity versus time graph, I have an acceleration here. That means my velocity is increasing, right? It's going from 1 meters per second to 2 meters per second to 3 meters per second as time goes on. Okay, so that is a change in velocity. If I had a velocity versus time graph that looked like this, what would my object be doing? It would be staying at constant velocity, right? And so the acceleration there would equal 0, right? If the slope is 0, that means acceleration is 0. Do we see the connection between these two ideas now a little bit?
Yes.
Okay. So this is the equation for change in velocity. It's change in velocity over change in time. Okay. Acceleration, we already saw, can be positive and negative. Okay. It can be both positive and negative. Does negative acceleration always mean that something is slowing down?
No.
No. No, it does not. Okay, it does not. So let's look at our graph again. If I have a velocity versus time graph, velocity versus time. Okay, sorry, velocity is on the y-axis there. I don't mean to make it look like it's on the x-axis. Velocity versus time. Okay, if I have an object that is doing this, what is it doing here? It's moving backwards, and is it speeding up or slowing down? It's speeding up in the backward direction. But our acceleration is negative because it's going, we have a negative slope. Okay, so we have got a couple different things that we have to look at here in terms of the sign of the acceleration. And I have a little bit of a way that you can maybe remember when acceleration is going to be positive and when it's going to be negative. Okay? So here's the rule of thumb for acceleration and the sign of acceleration. Okay? If an object is slowing down, if and only if an object is slowing down, the acceleration is in the opposite direction of the motion, or the opposite direction of the velocity. We could even say that, of the velocity. Okay, so when an object is slowing down, the acceleration is in the opposite direction of the velocity. Okay, which means it has the opposite sign. So let's look at it on a graph first. Velocity versus time graph. What is my object doing in this velocity versus time graph? Slowing down in what direction? We're in the positive direction here? Negative direction. We're below the x-axis. So our velocity here is negative. It's going in the backward direction, yeah, but is it slowing down or is it speeding up?
Slowing down.
Rethink here. Slow down a little bit your answers, right? Here's 0 velocity. So it's slowing down in the negative direction. Do we see all that? Okay, it's in the negative direction. It's below the x-axis. It's approaching 0 velocity, which means it's slowing down, right? It's going from negative 10 meters per second to negative 5 meters per second, now 0 meters per second. Okay, so in this example, we're slowing down in the negative direction. What is my acceleration here? Is it positive or negative? It's a positive acceleration, but a negative velocity. Yeah, and because our slope is positive, that's what I'm trying to show you here. Slope's positive, so we have a positive acceleration. So this confirms our rule of thumb, right? If an object is slowing down, our signs should be opposite. Okay? We can prove it mathematically using this equation as well. Okay, so let's look at this equation. If I want to solve for my acceleration, let's say that my initial velocity is 20 meters per second, and my final velocity is 5 meters per second. And let's say I did this, or I changed my velocity over a period of 4 seconds. No, not 4 seconds. 3 seconds. Okay, let's plug it into this equation now. What does the delta mean? Good. Change or final minus initial. Very good. So we're going to take final minus initial over time. Okay, so this is another example here. Am I slowing down or am I speeding up? Going from 20 meters per second to 5 meters per second. Am I slowing down or speeding up? Slowing down, right? 20 meters per second is really fast. 5 meters per second is not. Okay, so I'm going from 20 to 5. That means I'm slowing down. So that gives me negative 15 over 3, which gives me negative 5 meters per second squared. Yep, meters per second, or meters per second squared. Very good. Okay, so my acceleration is negative 5. My velocities were both positive. Does that match our rule of thumb? Yeah, because we were slowing down. Okay, so mathematically you can prove it. On a graph you can prove it. Those are just, that rule of thumb is just kind of an extra little thing for you to remember to check yourself. My acceleration should be negative here, or it should be positive, or blah, blah, blah. Okay? Questions about that? Okay. Oh, sorry, units for acceleration we mentioned briefly, but they are meters per second squared, or kilometers per hour squared, or whatever you want, but basically it's distance divided by time. Okay, or distance over time squared. It could be a lot of different combinations of those things, right? It could be kilometers per hour per second, or centimeters per second. There's lots of different ways that you could express acceleration, because there's lots of different ways you can express velocity and time. Okay, most often we're going to use meters per second squared. All right, let's try one here. Okay, get written down what you need to or what you would like to, and then we'll go through it together. Yeah, if you're ready, go ahead and solve it. I'm gonna walk through it together too, but you can go ahead and solve it if you'd like. It tells us we increase our velocity from 5 meters per second to 7.5 meters per second. Which of those do we know is our initial velocity? 5, good. And initial velocity we label as v sub I. Okay, so we know that is 5 because it says it increases from 5. So our final velocity then is 7.5, good. And the time that it took us to do that was 1.25 seconds. Average acceleration, we're always going to be solving for the average. Okay, so our acceleration is equal to change, which is final, minus initial over time, which gives me 2.5 over 1.25, which gives my acceleration equal to 2 meters per second. Very good. Okay, the reason it's meters per second squared is because our velocity was measured in meters per second, and our time was measured in seconds. Okay, so if you take meters per second divided by seconds, that's how we get that meters per second squared. Let's try this one here. Marissa's car is moving at a speed of negative 28.6 meters per second. She slows down to 24 meters per second over a time period of 3.2 seconds. What's my acceleration? Before you start looking at this problem, can you predict the sign of your acceleration in this case? It's going to be positive, right? We're slowing down, and that means our acceleration and our velocity should be opposite signs. Our velocities are both negative here. Okay, so our initial velocity is equal to good, negative 28.6. Our final velocity is equal to negative 24. Our time is 3.2 seconds. So my acceleration, I want to take my final velocity, which is negative 24, minus my initial velocity over 3.2. What happens when I have two negatives next to each other? they become a positive. Okay, which gives me, tell me one more time.
1.4375.
Is the final answer, or what's just the addition part?
Oh, sorry. 4.6 divided by 4.6.
4.6, thank you, divided by 3.2. Gives me an acceleration equal to?
1.44.
Great, 1.44 meters per second squared.
Mine just so
Are not the same thing. Do we understand that these are not the same thing? They're both rates, but they measure two different things. So what does velocity measure? The rate at which what changes? Good. The rate at which position changes, or the rate at which your displacement changes. Okay, same thing. And what does acceleration measure? The rate at which your velocity changes, or speed. Yeah, the rate at which your velocity changes. Okay, so velocity is telling us how fast our position is changing. Acceleration is telling us how fast our velocity is changing. Okay, so acceleration is telling us with each second my speed is increasing by 1 meter per second, or by whatever. Okay.
velocity is the.
Try this one on your own. Let's get the acceleration in meters per second squared. Meters per second squared, I want the acceleration in. Okay, which means the first thing that you need to be doing is converting those. Good. First thing that we need to do is convert that 75 kilometers per hour. So if we use the shortcut, we take it times 0.2778. Do any of you use the shortcut? No? That's fine. Okay, and I got 20.84 meters per second. Okay, or somewhere close to that. That's fine. Yep, that's perfectly fine. I had 835, so I just rounded. Okay, good. And is that our initial velocity or our final velocity?
Initial.
Initial, very good. And how do we know our final velocity?
It comes to a stop.
Comes to a stop. Very good. Comes to a stop. So it's 0. Yeah, 0.
So does the shortcut work for everything?
Every time you go from kilometers per hour to meters per second, you could multiply by 0.277. If you have to go the other way, just divide by 0.277. Yep. Let's plug this in. If we have acceleration equal to final minus initial, that means we need to go 0 minus 20.84 divided by 5. That means our acceleration is negative, what, 4.12 or 4.2 you said, or 4.17?
I got 1.7.
Either way, 4. That's fine. Okay. 4.2 meters per second squared. Yeah, it is. You're right. I'm sorry. You're right. Good. Very good. These are called our kinematics equations, and we are going to use these a lot. So if you would like to come get an equation sheet, you can grab one of these quarter sheets up here to write your equations on. That way you're not having to flip through your notes all the time. That might be a good idea. First of all, what does the term kinematic mean? Kinematics. Does anyone know?
Kinetic.
Something with motion, exactly, okay? That prefix kin, or kina, right, means motion. So the kinematics equations for constant acceleration, we're going to get these kinematics equations, we're going to get 3 that we really commonly use. I might give you the 4th one. I haven't really decided yet. But there is 4 main ones. We really only use 3 of them. But we're going to use these a lot, okay? So the equations are valid only if we know we have constant acceleration. Okay, so things are moving at a constant, or speeding up or slowing down at a constant rate. Okay, so we can only look at constant acceleration portions of time here. Okay, so basically what I'm saying here is if we have a velocity versus time graph that looks like this, Okay, lots of different things going on. We're speeding up, then we're slowing down, then we're staying constant, then we're doing this. We would have to look at each of these time periods individually if we're trying to do these calculations. We can't look at the object as a whole because there's too much variance in our motion. We want constant acceleration for these equations to work. Does that make sense? Okay. So here is our first kinematics equations. It's the easy one. This is the easy equation. Okay, and V sub F stands for velocity final or final velocity. Good. V sub I means initial velocity. A stands for acceleration. Good. And time. Okay, the thing about these equations is that you have to have units that are consistent throughout the entire thing. So if your velocity is in kilometers per hour and your time is in seconds, can you plug those in and let this equation work? No. Okay, your acceleration, your velocity, and your time all have to have consistent units. Consistent units. And honestly, most of the time, those units are going to be meters per second squared, and seconds. So let's practice one with this equation. Okay, so this says a bus is traveling 30 kilometers per hour. It speeds up at a rate of 3.5 meters per second squared. What velocity is it at 6.8 seconds later? Okay, so let me kind of show you how we can go about solving these problems, or what I think the best method is to start solving these. Okay, sorry. So first thing that we want to do is I want to start picking out our variables. And when I work with problems that I'm using these kinematics equations, I want to make a list of my variables in our margins. Okay, so on your paper, I think it's good to kind of just start making a list of your variables over on this section of the page. So let's start picking out what variables we think are what. Okay? Yeah, okay, Wyatt, tell me one.
Initials 30, 0,
Initial what?
initial velocity.
Good. Initial velocity is 30 kilometers per hour. And we're going to deal with that kilometers per hour here in a second. I'm just going to start making my list. Okay, Sergio, can you give me one of the variables? Final velocity is 3.5?
No, it's an acceleration.
Yeah, that's the acceleration. And how do we know that that's the acceleration?
Because it speeds up.
And it speeds up, yeah. But we most importantly know because of the units. Listen, I need you to understand that units give you big clues about variables in these problems. So meters per second squared, you know, is not a velocity unit. It's an acceleration unit. So we know our acceleration is 3.5. Okay, Candace, can you give me one other variable? 6.8 is what? Time, good. And what are we solving for here? Final velocity, very good. Okay, so I just like to put a question mark about what I'm solving for. Okay, so now we've got all of our variables picked out. We need to change this kilometers per hour to meters per second.
8.3.
Okay. We're saying 8.33 meters per second. So let's plug in VF equals VI plus AT. We're solving for velocity final. Our initial velocity is equal to 8.33. Our acceleration is 3.5 and our time is 6.8. So all we're doing here is solving for final velocity. So we're going to use your order of operations, right? Multiply these two first. Then we would add it to 8.33. Okay, thank you. 32.13, is that what you told me? Okay. And here, do we include a cardinal direction? No, because we weren't starting with 1. That means our velocity is positive, so we're traveling in the positive direction. Okay, that's all we really need to know here. If we were starting with a negative velocity, that would be our direction as well. If it had said we're traveling north, then we would include that north on our answer. But since we weren't given that, we're just going to leave our answer as positive 32.13 meters per second. Just a little bit. Okay, so this equation should go on your equation sheet as well as in your notes. This is just the second kinematics equation. So they don't really have names. We just have 3 kinematics equations that we use. This is the second of the 2. Or of the 3, I'm sorry. And realistically here, are we ever going to have time final and time initial? No, so you don't have to include that F subscript. I did it just because your book does, but I won't ever write that when I am doing my problem. So that's how your book shows it, just for your reference, but I don't include that time final because we're not ever going to have initial and final time. So let's think about what these variables are meaning here. What's D sub F probably stand for? Distance or displacement, right? Final displacement. Okay, or position. So what are the units for final displacement probably going to be? Meters, right? It's probably going to be in meters. What would D sub I stand for? Initial displacement. And units should be meters. Good. Okay. What do we know V sub I is? Initial velocity. What's our units for initial velocity? Meters per second. Okay. T is time. So it's in seconds. 1/2 A is acceleration, right? And it's what's the units for acceleration? Meters per second squared. And time, again, is seconds. It's important for you to understand on this equation that only the time variable is squared. Okay, and here the number is actually squared. It's not just the unit. The number here is squared. So time is squared. It's not the whole term here. It's only the time. Okay? Down here I wrote a little note. Most of the time D sub I, or our initial displacement, is going to be 0 because we're going to make the origin of our coordinate system basically the start of our motion. Okay, and I'll show you kind of an example of that. But we're going to always basically say that our starting position is 0. We're going to end up 50 meters from where we started, or whatever. Okay? Let's look at an example here. Okay, a train accelerates from rest at a constant rate of 3.15 meters per second squared for 1.57 minutes. How far does it travel in this time? Okay, so get written down what you need to, and then we will work through this together. Good? Yeah, good. Initial displacement is 0. Okay, Sergio, can you give me one?
3.15 meters.
Acceleration, good, is 3.15. Okay, Brendan, can you give me one?
Time is 1.57 minutes or 94.2 seconds.
Good, thank you. Minutes, and you said 94.2 seconds? Is that what you told me? Yeah?
Yeah.
Is that what you told me? Okay, sorry. I just wanted to make sure. Okay, what else do we know? We know one more. Good. Initial velocity is 0. Okay, so these problems will give you clues in the context, right? So you have to make sure you read. It's not just looking for numbers. So V sub I equals 0. Do we have enough variables now that we can solve for final displacement?
Sure. Yep.
Okay, we want to solve for final displacement. I like to put the question mark there just so I know what variable I'm really looking for. Okay, so D sub F equals 0 plus 0 times time plus 1/2, 3.15, 94.2 squared. Okay, remember, just the time is being squared here, so 94.2 should be squared. Anything times 0 is 0. Right, so we don't have to include that. It's easy enough, right? 0.5 times 3.15 times...
Half of them are zeros.
That's right, when half of them are zeros, it does make it a little easier. Okay. Get a pretty big number or a pretty small number? Pretty big, all right? I got about 13,975.98 meters. All right, I want you to go ahead and try this one on your own. I want you to try this one on your own. Same equation, except this is a two-part problem. Okay? It's all right. You can do it. Okay? It tells us a driver brings the car to a full stop in 4 seconds. It was initially traveling at this speed. You have to find the acceleration first, and then you can plug it into this equation to solve for your distance final, your displacement final. Okay, so it's two parts. I think you can do this part on your own.
So we don't know the distance initial time, do we?
Distance initial is just 0. Because we're looking at basically when the car starts braking, that's going to be kind of our starting point. So that means we're going to set the distance there as 0, and we're going to find out how far it's traveled from there. Okay, so to solve for acceleration, I'm going to use this equation, VF equals VI plus AT. This is the same as doing it like this. Okay, so velocity final is 0, 25.24 plus A times T. Okay, I should subtract this over. Negative 25.24 equals 4A. So now I'm going to divide by 4. Thank you. Negative 6.31. Do we all agree on our acceleration with that? Negative 6.31?
Yeah.
Tell me what? Now that I have my acceleration, I can plug it into my kinematics equation to solve for distance final. Okay, now I'm solving for dF. I know my initial displacement was 0. Okay, because as my car starts to come to a brake, we're making that basically our new starting point. We want to find out how far it travels from when it starts to apply the brakes to when it comes to a complete stop. So 0. Can we drop this next term as 0? No, because we have an initial velocity this time. We have an initial velocity, so it's 25.24 times time plus 1/2 negative 6.31 times 4 squared. Okay, so mathematically, just use our order of operations here again. Do we all agree here with 50.48 meters?
Yep.
That's how far it traveled during that time. So these kinematics problems could take you 2 steps, right? You might have to solve for something to solve for something else. That's okay. That's why making the list is so important, because if we see here that we have no acceleration, we can't solve any of our kinematics equations without acceleration. Okay, so it might take more than one step. Here's your third kinematics equation. Okay, car starts at rest, speeds up at 3.5 meters per second after the light turns green. How far will it have gone when it's traveling 25 meters per second. So it doesn't tell us how long it takes to speed up to that final velocity.
No.
It doesn't matter, right? We can still solve for final displacement here, or how far it travels. Okay? Okay, so let's pick out some variables here.
So would initial distance be 0?
Uh-huh. Initial distance or initial displacement is 0 because we're looking at the time frame or the picture basically when this car applies that gas pedal and when it reaches a speed of 25 meters per second. We want to find out how far it's traveled during that time. Okay, Miguel, can you give me one of the variables?
The final velocity is 25.
Yep. Good. And Keaton, can you give me one?
Acceleration 3.5 meters per second squared.
Good. Sergio, you got another one? Initial velocity is 0. Perfect. Perfect, perfect. And tell me what we're solving for, Sarah. You're right. You're right.
Final velocity squared.
No, we have final velocity. Okay, so tell me what's that question asking?
Far would have gone per second.
Okay, so what do you think we're looking for here? Yeah. Final distance or final displacement. Okay, so d sub f is the variable that we're solving for.
So basically just put all those into the second equation.
Why the second one?
Because we're solving for final distance.
But in the second equation, we have to have time. Do we have time? No. So we could solve for time, then plug it into the second equation, but we can solve this equation because this has distance final, velocity final, velocity initial, and acceleration. We have all of those things.
Then you're gonna like switch it all up.
You're gonna have to, yes, you're gonna have to rearrange the equation to solve for a variable.
This gives you take acceleration divided by 25, that's your time. Square root.
No.
How would you find time?
If you wanted to find, okay, so our final velocity squared is 25 squared plus, oops, no, it's not plus, equals 0 squared plus 2, 3.5 df minus 0. Distance?
No, the final distance.
Nope.
Since you have to subtract it to the other side.
No, we won't subtract it. We're going to end up dividing it over. Okay, so this 0 drops. 25 squared is 625 equals 7 df. Right? And since this is minus 0, the whole thing over here is minus 0. So we don't need that either. So now we have 625 equals 7 times df. So we're going to divide by 7. Divide by 7. And distance final then is equal to,
89.28, or you could say 29.
thank you.
I did the other one at 89.2.
Great. Yep. It's okay. Rounding things are no problem. Yep. Okay. Questions? Feeling okay?
Yeah.
All right. So let's pick out our variables here.
Initial velocity is 15 meters per second.
Good. Initial velocity is 15. Final is 25. Very good. And what do we know about this?
Final distance.
Distance final. Good. And then distance initial would be 0. Very good. Solve for acceleration first, and then we can solve for time.
Delta V over
Nope, we have to use this equation to solve for acceleration. Right? We have final velocity, we have initial velocity, we have both of these, we're going to solve for A.
Is this a different?
No, this is still the third one.
Oh, yeah, I
So 25 squared equals 15 squared plus 2a. 125 minus 0. Okay, so algebraically our next step's going to be to do what? Subtract this over first. Equals 250 times a. Right? Because I need to take 2 times 125. Are we seeing that? Then we can divide over that 250. So A is equal to 1 point what? 6.
Meters per second squared.
So are you done with your problem now?
No.
Now you have to find time.
Easy problem.
You can use the easy equation now to solve for time. So in this problem, it didn't even tell you what's your acceleration, or it didn't ask you to solve for acceleration. You need to understand that if you're missing an important variable, such as initial velocity or acceleration, those are in every equation that you might have to solve for those. Okay?
Basically, you're just figuring out what you have and find what you don't.
Exactly.
What's 10 divided by 1.6?
That's what your calculator's for. So now we can go back and use our easy equation to solve for time. So VF equals VI plus AT. So and we got what for our time?
6.25 seconds.
Okay, very good. Okay, so try this one on your own. I'm not giving you the equation this time, so you need to do some problem solving. Make your list, see what you have, see what you don't have. Try to problem solve here.